Right, let's see if I can use linear circuit builder. So I'm going to fire up NEURON, just right. So we're going to do this from scratch. NEURON GUI, right, and we're just going to build a world's simplest cell, right? So we're just going to do single compartment um, with all the good stuff in it, and we might as well bring up a just to make our lives easier. We're going to put in um, a current clamp electrode. And we might as well also bring up the run control. And we'll set t-stop to be something vaguely useful like that. So then we can have 50 milliseconds of delay, 100 milliseconds long, and like 0.05 if memory serves. Let's just check that works. Right, so we're going to go graph, voltage axis, and run. Wonderful. Good. Okay, so now let's get into the sort of the difficult bit. So we're going to go build linear circuit. I'm far from an expert in this, right? But I know enough to sort of get things going. So the first step is we want to put we want to get electrical access to the cell, right? And so you've got your single electrode axis and your two electrode axis, right? So we're going to put that there. You can move it around. Looks a bit bung. We're going to put it sort of in the bottom left because we're going to put all our circuit elements up there. And then the first thing we're probably going to want to put in is an op amp that always comes out massive, and you can shrink it a little bit and make your life a little bit easier. Because typically, if you've had to resort to this, you're going to be building a moderately complex surface circuit, and you want as much space as you can. So just to sort of prove that things are vaguely working, what we're going to do is we're just going to create a voltage follower amp or a buffer or amplifier, right? So it's just going to be the voltage out of the amplifier is equal to the voltage into the cell, right? So you may or may not be familiar with this circuit topology. If you're just a pure electrophysiologist, there's no shame in not, but this circuit here basically just says the output here is always going to be exactly the same as the input here, and the input here comes from out of the soma, right? Now, that's kind of about as simple as it gets. So just like if you're using the cell builder, you go through these steps in order, and a lot of the steps you can just skip. So you can go to label. So we can move. We've only got one label here, so we're going to change it to, let's just call it buffer amp, right? Cool. That was pretty useless, but we're just going to do it just so people know what it's doing. Then parameters. Now, parameters can be pretty useful. In this instance right now, there's no parameters worth changing, so we're just going to forget about it. And then we're going to simulate, most important bit. There is a issue that I do not know the way around, which I'm going to show you second. And it's pretty important, and so I love it if somebody could tell me what to do about this, right? So we go new graph, plot what, just like you were doing in a normal graph, and we're going to say we've got these options: 1, 2, and buffer amp. These will respond to the voltages at certain nodes, right? So this whole wire will have one voltage, all of this wire will have another one. This one refers to the voltage here, or there, 2 refers to the inverse. But I don't never know how to tell which one's which because you can't label wires. And just to prove that I'm not crazy, right? We go label, we go change. Yeah, clicking doesn't do anything. So I've never really understood what you're supposed to do here, apart from ground a wire that you're interested in and hope that you still get some signal everywhere else, and then you know that it's yours, right? So we're gonna play with that in a second. Anyway, so we go back to stimulate, we go new graph. I think I drew this one first. Or did I draw that? No, I drew that second. So I think this is going to be 1. So we're going to go plot what 1, and if the world is good and fair, when I go in it to run, the signal that's over here, view equals plot, should be the same as this. Looks like it is. That is great. Okay. But right now, I could not blame you if you did not believe that I had done anything at all. So let us, instead of making this a buffer amplifier, let us now make this a preamplifier. Let us actually amplify the signal. So we're going to go back to arrange. We're going to grab our wire and we're going to yeeted off into the distance. We're going to get rid of that one too. And so let's put a feedback resistor and a resistor to ground. And we'll put ground there. And then we'll connect up our wire from there to there. And we have now made a two-fold amplifier, because basically the whole point of this op amp is it's trying to make this inverting terminal, this input here, the same as this, the voltage being equal. And in order to do that, actually has to put the voltage here being twice the voltage here, because it loses some voltage here and some voltage there. So you get sort of half the voltage there as you got there. And so then if this is half of that and this must be that, then this is double that. I think that made sense. Right, doesn't matter if it did or it didn't. We've changed it now so that if we look at the voltage, it should be twice what the cell is actually providing. So go back to simulate. Actually, let's just check out parameters first. Parameters, right? So we've got these R9 and R8. Let's give them sensible numbers, shall we? Right. So this R9, I was taught to call that RG because it's the resistor to ground, and this one here is RF, which is feedback resistor. And now when we go to parameters and click parameters, you can see. Let's just leave that. So we've got the gain on the amplifier, the time constant of the amplifier, which I think is just part of the simulation rather than a real property you'd ever see in a data sheet for an amplifier. But importantly, here are our mega ohm resistors here and here. If you're making this amplifier for real, you probably wouldn't use those values, but the point is they're equal, so this is going to be a 2 times amplifier. Yeah, so we can close that. We go back to simulate. We want to do a new graph, and what do we want to plot? I think it's still, sorry, plot what? I think it's still voltage 1, but we'll have to do a investigate. Init and run, view equals plot, and it's not voltage 1 because you can see this is basically the same as this. Okay, so let's not plot that, let's plot 2. Init and run. No, okay. I'm pretty confident this is going to work, but I'm starting to get nervous. Plot what? Let's do 3, which hopefully is going to be the voltage here. There we go. Right, view equals plot. So here is our 2 times amplified voltage. And the reason I'm doing this is because someone has been asking about pipette capacitance, right? So we can crudely simulate pipette capacitance, or slash accurately, but pretty crudely, but it'll do for this demonstration. We go arrange, we put in a capacitor from here. So this is our electrode into the cell, feeding into our amplification circuit, and we'll put a ground on the other side, and we're going to label it, and we'll call it like something nice like CP, right? Accept. And now, of course, anytime the voltage in here changes, there will be a current proportional to the rate of change, which will essentially suck the current out of the cell every time the voltage changes. Now, there's no series resistor and there's no input resistance of the amplifier, so this is not exactly accurate, but it should still work. So we go to parameters, we edit the parameters for CP, which is in nanofarads, right? And it's 1 nanofarad, which would be a hell of a pipette capacitance. So let's just put this to like 0.001. And we go to the simulate, we go new graph, let's plot our output, which is voltage 3, and we go init and run, and let's look, actually, we'll go keep lines here, so we can see what it used to look like. So this is the recording, the true voltage inside the cell here, right? This is not anything coming out of the cell. This is of course relevant because pipette capacitance truly does suck the current out of the cell during, well, in a rate that's proportional to the change in membrane potential, the rate of change of membrane potential. So if we go in it and run, let's have a look. Subtle shift, right, to smaller and later action potentials. Now let's ramp this up to, again, quite a plausible value, init and run, and look, we're completely destroying everything. Now, and if we go view plot, you can see this is what we're seeing, except it's twice the true values. So that is the very basics of how you use the linear circuit builder in NEURON. via the GUI. It's great for quick and dirty things like this. Again, I'm not an expert, right? There's a lot of things in here. There are some things like the initial conditions. Sources is if you don't want to do this quick and dirty version of applying current, right? So if oh, that's not coming up. Oh, is that connect? Anyway, you probably need to apply the batteries now that I think about it. Point is, a lot of these other things are a bit more self-explanatory once you can get the basics going. Hopefully that is of some use to somebody.